So I will welcome Aslan Tchamkerten. He is an associate professor at, it says Telecom Paris Tech, and then it says X, École Nationale Supérieure de Télécommunication, ENST. So maybe that's the former name.
I mean, it has changed 5 times names, so yeah. So we try to hide this.
I think the work he's going to talk about maybe started when he was a postdoc at MIT with Greg Warnell several years ago. I will note that he received his habilitation in 2011, but I don't actually know what that is. So maybe we'll select that. Anyway, I'm looking forward to it.
Okay. What I'm going to present is based on a joint work with Giuseppe Caire, Venkat Chandler, David Shea, and Greg Warnell. So this work spans roughly 9 years. So it has been a long-term project, which is seeing an end. We're just essentially concluding that work nowadays. All right. So here are 2 fundamental bounds that are provided by information theory. Okay, so the one is on latency, and the other is on energy. Okay, so if I have a file of B bits that I want to transmit, then I know that the minimum number of channel uses that I need is B divided by C, which is the capacity of the channel. Okay, so I cannot transmit this file of B bits with fewer channel uses. Okay? And similarly, so we have a lower bound on the energy, so the minimum number of joules that I need to put into my system to convey those B bits will be at least B divided by another constant, which is what is called the capacity per unit cost. Okay? So throughout the presentation, I'm using cost and energy exchangeably. Okay? For me, those are the same. Okay? So those are fundamental bounds on latency and energy, and we also know from modern coding techniques and some very recent work that those bounds are not only can also be achieved and very efficiently. Okay, so then the question is whether there is anything left for improving communication. Okay? So in order to answer this question, we need to revisit some of the fundamental assumptions that information theory makes, and one of them is the one of perfect synchronization between the transmitter and the receiver. So probably most of us have seen an information theory book, and we know that essentially all the books on information theory all have this implicit assumption of perfect synchronization. So the assumption, which is usually hidden, is the following. The file that you want to transmit, the B bits, are available at time 0. Communication takes place between time 1 and time n. Decoding always happens at time n. And yeah, the receiver just gets a noisy version of whatever the receiver or the transmitter sends. Okay? So, and really what modern coding techniques do, they really overcome the vertical uncertainty of the channel that is caused by the noise. Okay? But there is no such thing as horizontal uncertainty. I'll forget about that. All right, so when is the assumption of perfect synchronization reasonable? Well, it is reasonable to assume perfect synchronization when the number of bits that you want to transmit is big compared to the timing uncertainty. Right? If I have to send a video, it doesn't really matter if I have to spend a little bit of time to synchronize with the receiver, because that little overhead will be amortized over many channel uses. Okay? But if you consider the opposite regime, namely I have to send a few bits once in a long while, periodically. So think, for example, at control types of application or sensing type of applications. I don't necessarily need to send gigabytes, right? Just a few bits sporadically once in a long while. Okay? So in that regime, it's not clear if I can still forget about the impact of asynchronism. Okay? So I'm going to focus precisely on this regime. So this brings me to the focus of the talk. I'm going first to address the question as to how to quantify the level of asynchronism in a communication system. Okay? What does it mean for a system to be more asynchronous than another one? Second, I'm going to address the question as what's the impact of asynchronism on latency and energy. And finally, I'll address the last question, which is whether we can easily tweak communication protocols that are for synchronous systems to work also for asynchronous systems. Okay. All right. So the talk will be will be divided into two parts. I'm going first to address the energy problem. Okay. So I want to send bits as reliably, but using as few bits as possible, and I'm going to evaluate the impact of asynchronism. And the second part of the talk, I'm going to address the latency problem. Okay, so how to send data quickly without taking care of energy. All right, so let's remind what we know about energy-limited communication for synchronous settings. Okay, so this topic was studied by Verdu and Gallagher in the late 80s for the discrete membrane-less channel. Okay, so here's the model. We have a discrete membrane-less channel which is characterized by a conditional distribution, x and y. And they model the energy constraint as a cost, right? So you associate to each input you have a cost, which is simply a non-negative function. And once you have this, so for example, k of x could be x squared, okay, to model the energy. And then once you have this, you define what is called the rate per unit cost, which is simply the number of bits that you want to transmit divided by the cost to transmit those bits. Okay? So we take here, so k of c and m is simply the sum of the individual costs of each component associated with the code word of message m. Okay? So I'm taking here m, the maximum over all messages. I could take the average, the results would be the same. So rate per unit cost, this means how many bits I can send per unit energy. Okay. And then naturally I'm interested in the supreme of those rates, which is called the capacity per unit cost. And here is the result that they derived. Namely, the capacity per unit cost is simply the maximum over all input distributions of the ratio of two things, the input-output mutual information and the expected cost. Okay. And what they also showed is that although the block length, so the size of the code word that you're transmitting is an implicit parameter, they show that we don't need to have huge code words to send data. It suffices to consider block length that grow linearly with the number of bits. Okay, so in a sense, this is optimal. All right. So now I'm going to talk about the asynchronous communication model. So I'm going to present it very gradually because it's, I hope to convince you that it's very natural. But it has a few more parameters, and just to build the intuition, I'll first start with a general overview of the model, and then go into detail and speak about the transmitter, the channel, and the receiver more specifically. All right, so here are the basic features of the model. The first, so the model, what it captures that data is available at a random time at the transmitter. Okay, so since the transmitter and the receiver are operating asynchronously, right, we assume that data is available at a random time, unknown to the transmitter. Second, we will allow the transmitter to choose when it actually wants to send data. Okay? Namely, once data is available at the transmitter, we don't require the transmitter to start sending that data right away. Okay? So the transmitter, if it wants, can choose to delay information transmission with respect to the time when information is available. Okay, so we will allow that degree of freedom. Outside the information transmission period, the transmitter stays idle, right, and which means that the receiver observes pure environmental noise, pure noise. And since the decoder doesn't know when data will be transmitted, it makes no sense to consider fixed length, the decoding at a fixed time. So we'll consider a sequential decoder. Right? So the decoder will be in the listening mode. We'll listen at channel outputs. And at some point we make a decision. Say, aha, the transmitter wanted to send me message block. Okay. And finally, I'm going to consider a discrete time model where the time scales of both the transmitter and the receiver tick at unison. Okay, so, yeah?
Sorry, didn't mean to interrupt. And when you say the transmitter can choose when to start sending information, do you have any constraints on that at all? Because I could envision in the limit the transmitter waits until the end of time,
yes,
and then transmits gazillion bits, and you're back to the...
Sure. I will address that question. Yes, I will address that question in the next slide. All right, so let me just, actually in a couple of slides, let's bear with me for a moment. Yeah. So efficiency criteria. So how do we, what are our efficiency criteria? So the first will be the input energy. Right? So this will be modeled in exact same way as for synchronous communication. We're going to associate a cost to each bit that we are sending across the channel. But what we also do, we are going to put the constraints on the receiver, right? So this is less common. So we're going to have a cost at the receiver. And so what is this cost? Well, there are many ways to define the energy constraint at the receiver, but what we chose as the following is that, so the motivation is that since the analog to digital conversion is one of the most power consuming functions, what we want to minimize the sampling rate. So what that means, it means that the receiver has to make a reliable decision on the transmitted message by looking at as few channel outputs as possible.
Including the timing?
The timing doesn't know about timing. It doesn't know about timing.
So he has to find it.
It has to find it, yes. But basically, so the receiver, yeah, it will look at, it will sample as few channel outputs as possible. So this is what we want, and yet be able to reliably detect and decode the transmitted message. Okay. So this is sort of an overview of the model. So let me be more specific. I'm going to discuss about what's happening on the transmitter side, the channel, and the receiver. Okay. Transmitter. The data, which is to be transmitted, is available to random time nu. And this time nu, we assume it is uniformly distributed between time 1 and time A. Okay, so random time. Okay, so this line here represents time. So A is a known constant to everybody, and it characterizes the level of asynchronism in the system. Okay, so if A is equal to 1, we are back to the synchronous case, right? Because there is no timing uncertainty. And if A is, the larger the A, the more asynchronous the system. Okay. So this is new. Now, once data is available, the transmission starts at a time sigma, which may depend on two things. One, on the message that needs to be transmitted, and second, on nu. Okay, so the sigma here is a function of the time when information is available and when the message and what message we want to convey. Okay, so we allow this degree of freedom. So we don't require sigma to be equal to nu. Okay, so in principle, the transmitter can choose to delay information transmission. I haven't addressed your question yet. I'll soon come to that. So let's talk about the channel. So the channel is, we'll assume it's a discrete memoryless channel. So whatever is sent across from the transmitter will go through a DMC and get received by and observed by the receiver. So the channel is a discrete memoryless channel, which is characterized by an input alphabet, X union star, and an output alphabet. Now what is X? So X, this set here, corresponds to the set of symbols that can be used for codebook design. Okay, so when you design your code words, they can use only symbols from this set. Okay. And the star symbol, well, the star symbol induces, models the output distribution when nothing is sent. Okay, so it's a pure noise distribution. So the pure noise, when outside this transmission period, meaning over here and over here, what the receiver gets is IAD samples of a random variable y, which is distributed according to Q of dot given star. Okay. So just, I mean, this may be somewhat curious for certain people. I mean, it's not that the transmitter is sending a star across the symbol, but in information, so outside information transmission period, the transmitter stays idle, which means that it does nothing, but in information theory, there is no such thing as nothing. So nothing means no information, and no information means a constant symbol. Okay, so, and the constant symbol here is the star. So, so the star, just should emphasize that the star is not a degree of freedom of the transmitter. It's really a part of the problem, right? If we are communicating across, for example, a Gaussian channel, it is natural to consider the star as the zero symbol, right? So when there is nothing is sent, the receiver gets just pure IAD an IAD sequence of zero mean random variable.
Well, the cost of the star is zero.
I'm going to address this question also in a couple of slides. Yeah.
So but I mean, I could use the star to break up the code word, right? I could
Well, I will talk about this later. Yes. So
yes,
but yes. So here is something. So I'm going to distinguish. I'm going to consider two cases, namely for certain the case where star is included into X, in which case I can use. I have a zero. I have a free symbol at my disposal, and the other case where the star does not belong to X. Okay, so for example, just the fact to be, whenever you are awake, it may be costly already. Right? So yeah, so let me capture that setting. All right, so let's see what's happening on the receiver side. So the receiver for the synchronous communication is just a decoding, it's just a function, right? It maps output vectors and map those output vectors to messages. It's just a function. Now, here in the context of asynchronous communication, there are two extra features, which is one, a sampling strategy, which will tell the receiver what samples it should look at, and also a stopping rule. Okay? So the stopping rule will tell the decoder when it should make a decision about the transmitted data. Okay? So the sampling strategy will be either adaptive or non-adaptive. So a non-adaptive sampling strategy is a strategy where the times of sampling are known before communication starts. Okay? So they are completely independent of the channel outputs. By contrast, a sampling strategy is said to be adaptive if the next sampling time is a function of past samples. Okay? So depending on the samples that I have observed so far, I may decide to skip the next few and then look at the next one. Okay? So for example, here I'm sampling at time t. I decide to skip this one, and sampling this one. Okay? Now, once you have decided on your sampling strategy, you define the stopping rule. So the time when you actually make a decision. Okay? So mathematically, the time when you make a decision is a stopping time, which is defined on top of the sampling strategy. Okay? Which will so it's a causal. So tau is a causal function that tells you when you should stop and make a decision. All right.
Sorry.
Yeah.
One more question.
Yeah.
You're probably going to say it later, but are you considering the possibility of encoding some information in the value of sigma?
Yes. Totally. Yes. You could do that in principle. Absolutely. Yeah.
The value of sigma?
Value.
The value,
Oh,
yes,
the
because you
value.
can play with timing. You can play with time. Yes, you can play with timing. Absolutely.
House position modulation.
Yeah.
Absolutely. Yes. Yeah.
So the notion that, like, you could say, I'm always going to decode at A, but I'm going to stop sampling earlier.
Yes.
Right?
So yes, I could do that. So let me address also. I'll address this problem of decoding at the very end. Actually, in the next, not this slide, the next one. Okay. So the energy constraints. Okay. So we have talked about the transmitter, the channel, the receiver. Then let's talk about the energy constraints. So at the transmitter, so we impose a cost to each input symbol x, exactly the same way as in Gallagher and Verdoux's case. Okay, exactly the same way. And the only assumption that we make is that there is only one zero-cost symbol, which is the star. Okay, so either star belongs to the set x, in which case I have a zero-cost symbol, or it doesn't. All elements x have a positive cost. So this assumption can be actually dropped, but I mean, it gives essentially unnatural settings. Okay, so let's stick with this assumption here. Transmitter, energy constraint, receiver. Okay, so as I said, we want to model, we want to put a constraint on the number of samples that are observed by the receiver, and here is how we impose that. We impose that the number of samples that the receiver observes up to time tau, up to the time when it makes a decision, divided by tau, should be less than rho. Okay? So what we do, we count the number of positions where the receiver makes a decision. We count the number of position, number of sampling positions. Okay? We normalize this by the time when you make this decision, and this should be less than a predefined constraint, predefined fraction rho. Okay? So for example, if you set rho is equal to a half, this means that the receiver should see only half of the channel outputs, okay, with high probability. Okay, is this condition clear? Yeah?
A little bit confused, why is it not that you count till A?
Well, because actually, because you don't need to count those, right? Why would you count until A? Because you stop here. The whole experiment stops here.
Okay, it is actually counting till A, but you could be dividing by A because your experiment is always till A.
You want to divide, or you want to normalize this by A?
Yeah.
Yeah, but we make these things more difficult here.
Right, but nothing happens before, like, you won't send anything before A expires, is that correct?
No, I will, in principle, if data is here, why should I wait until A?
Okay.
But I'm addressing now the question yes. Okay, so as I said, in this part of the talk, I'm just talking about energy and not about latency. However, to make it come meaningful, I had to talk a little bit about delay. Okay, so remember, we allow the transmitter to delay information transmission at its will. Okay, so for in particular, the transmitter could have sigma equal to A. You could delay information transmission to the very end. So if you do that, we are back to the synchronous case, right? Because the whole experiment ends at time A. Both the transmitter and the receiver agree that information will start being sent only at time A. So then there would be no loss. There would be no impact due to asynchronism, because actually it completely disappeared. Both the transmitter and the receiver always communicate at time A. Right? We could do that. However, the penalty would be in terms of delay, right? Because if data is available here, it's going to be delivered only at time A. And depending on the size of A, this may be huge, right? Maybe the delay then grows proportionally with A. Okay? So in order to have the problem meaningful, to avoid this weird situation, we impose that the elapsed time between when information is available and when it is decoded to be of the order of the number of bits that you want to transmit. Okay? So we impose the same communication delay as in the synchronous setting. Okay? So order of B. Remember, this order of B is the same communication delay as the one we get in the synchronous setting. Yes?
How does the receiver side know what that is?
Sorry, what the receiver?
How does the receiver side know what that order is?
Oh, we just want, so we'll just measure. It doesn't know a priori, it doesn't know, but I'm going to say that a communication strategy is eligible if I can guarantee that this delay here is within order of B with high probability. Okay? This is what I will, I can check, right? So I run the experiment many times. I always count the elapsed time between, I measure the elapsed time between nu and tau, and if it is order of B, right, then I say it's okay. Yeah. Any other question? Yeah?
So do you design tau yourself, or is it available to you?
Sorry, what is it?
So tau is the first time that the ratio of the number of bits and the time.
Yes. So tau is the time when you make a decision, when the receiver actually decodes. Tau is a decoding time. Mm-hmm. Tau.
So the first time that you have enough number of samples to decide.
Exactly. Is a time when the receiver said, I think I'm confident enough to make a decision, let me stop and output a message. Exactly.
So does the receiver know the rate, this rho?
Yes, the rho is known. It's a parameter, before communication starts, the parameters which are known as are A and rho.
But it doesn't know nu.
No, nu of course not, because otherwise you would be back to the synchronous case. Other questions? Right. So here is the objective. Now, given A and rho, find the capacity per unit cost, okay? Which obviously will be impacted by the level of asynchronism as well as the sampling constraint. All right, so let me present the results. So the first result assumes full sampling. Okay, so in this case, the receiver gets to know all channel outputs. Okay, can choose to look at all of them. And we assume that the star can be used for codebook design. So in that case, we have the following result, which says that the asynchronous capacity per unit cost is equal to the synchronous capacity per unit cost divided by a factor 1 plus beta. Now what is this beta here? This beta is the log of the uncertainty window A, the level of asynchronism, divided by B. Okay, so the measure of beta is the timing uncertainty per information bit. Okay. Now what this says, so there is a penalty in terms of capacity per unit cost only when beta is positive, right? Non-zero. So what that means, but when beta is positive, what does that mean? It means that the level of asynchronism is huge, is exponential in the number of bits that you want to transmit. Okay? So what does the scaling mean? It means that, for example, you are sending, say, a millisecond message every 5 minutes. Okay? So very few data, little data, every long time. All right. And if beta is equal to 0, namely, even, for example, if A grows, say, polynomially with the number of messages, then there would be no impact. The capacity per unit cost would be the same as in the synchronous setting. No loss. Okay? All right. So, yeah, I mean, another way to interpret this formula, if you invert it, right, the inverse of the capacity per unit cost is the minimum energy to send data. If you invert that equation here, you say that the cost to transmit B bits asynchronously is exactly the same as the cost to transmit B plus log A bits synchronously. Okay, so we have this characterization. And what we also derived is the minimum communication delay. Okay, so among all coding strategies that achieve the capacity per unit cost, some of them have a longer delay, some have a shorter delay, and the minimum delay, meaning the elapsed time between nu and tau, we found it. So it's what I call here d min of beta and rho. And so I'm not putting here the exact expression. So it's a function that grows indeed linearly with the number of bits, but which can be characterized. Okay? So I didn't put here the exact formula because it's a little bit unwieldy, but yeah. So this can be characterized as well. Here is a formula for the capacity per unit cost which holds in general, okay, regardless of whether the star can be used for codebook design. Okay? Namely, it holds also in the case where you cannot use the star, we have a zero cost symbol. Okay? So here is what the theorem says. So the asynchronous capacity per unit cost is equal to the maximum of all input distribution of the mean of two objects. Okay? Now what are those two objects? So the first object here, what is it? Excuse me? Yes, this is the synchronous capacity per unit cost. Okay, so this is the term, the capacity per unit cost. And indeed, if you flip the max and the mean, you get an upper bound, and this upper bound will be upper bounded by the synchronous capacity per unit cost. Okay. So what this says is tells you that the asynchronous capacity per unit cost is always at most the synchronous capacity per unit cost. It's a sanity check. Asynchronism cannot help you to reduce the energy that you need to put into your system. It's not. Okay? And this term here, so the intuition for that term is really, so what it captures is really, so it's related to a hypothesis test. This quantity here, and essentially it measures how difficult it is for the receiver to discriminate between pure noise and the data carrying message. Okay, so that's really what the red part means, and it is due to asynchronism. Okay? So it can easily be checked that if beta is equal to 0, the mean of those two quantities will be this one, and you will be back to the synchronous case.
So the result of the previous slide was a special case?
It's a special case of that, yes.
Well,
when star belongs to
belongs to the set of
to a set exactly. So I mean, it's not a one-line proof, but it can be deduced fairly easily. Okay, but this one holds irrespectively of that one.
And in the previous result, are you saying that, well, unless A is growing exponentially, there's no real penalty?
Yes. Absolutely, yes.
Should I interpret this divergence term as a what's it in source coding?
The divergent term here?
Yeah, I could interpret it as a excess rate in like the source coding.
Yeah. So this is so this whole term here can be written to one divergence term, and this divergence term here captures it's the large deviation exponent of the noise producing a typical message output. Okay, that's what this term here is. All right. So how do we prove this result? Well, achievability. We use random coding, a la Cover, Gallagher, etc. So transmitter, random coding, generate a random code, send it at time new. So we don't even need to delay information transmission and play with timing. We don't need that. And the receiver, what it does, it will use a sequential typicality decoder. So at each time, it looks at past n symbols and makes a decision whenever those past symbols look typical with one of the one of the converse. Okay? The converse is more involved. Okay, so we cannot just rely on Fan-Hoze inequality. Fan-Hoze inequality will just give you the blue term, the synchronous term, which we saw before. But in order to get the red term, you need to do more work.
So there's no notion of not sampling?
No, here it's always on the full sampling. I'm going to address the sparse sampling immediately. Sparse sampling. So first I'm going to talk about the non-adaptive case. Okay, by non-adaptive I mean that the sampling times are chosen before communication starts. Okay? All right. So intuitively, it may seem that, well, if I have a sparse constraint on sampling, well, it means that the receiver is almost sleeping, which means that perhaps I need more energy to transmit the same data. Okay? It turns out this is not the case. Okay? So the asynchronous capacity per unit cost under asynchronous exponent beta, so this beta here is this one here, under sampling constraint rho, is the same as the asynchronous capacity per unit cost on the full sample. So there is no loss.
But both sides know.
Both sides know the sampling times, exactly. So that's the catch, right? So that's exactly. So it's true the sampling strategy is non-adaptive, but both the transmitter and the receiver can choose those sampling time in advance. Okay? And we are strongly rely on that. We will rely on that. So no loss in terms of energy. However, there is a hit which is in terms of delay. So, okay, the penalty in terms of delay here. The delay when you have a sampling constraint rho is equal to the minimum delay on the full sampling, but multiplied by a factor 1 over rho. Okay, which means that, say, if the receiver sleeps half of the time, the reaction delay, so the time between nu and tau, will be multiplied by a factor 2. Okay, so it grows as inversely proportional to the sampling rate. And here note that there is a small distinction. If star belongs to X, we have this penalty here, and if star does not belong to X, we don't have a free symbol at our disposal, then we have an extra penalty, which is a little rho here. So the penalty is 1 plus rho divided by rho. So just a penalty in terms of delay, but no penalty in terms of energy. How do we achieve this? It's very easy. Suppose that your receiver can sample only, suppose rho is equal to a half, which means that the receiver has to sleep half of the time. Okay? Well, let's decide then just to communicate at even times. Okay? Then you can use the exact same code words as on the full sampling, and just stretch each code word so that now the components match even times. Okay? And in between the symbols, the code word symbols, you stick stars. Right? So this is the code word symbols, and in between you're going to put the star symbol. And the star symbol has 0 cost. Right? So doing the stretching procedure doesn't constant anything. So this is very easy, so we can do that. And indeed, if you do this, you immediately see that the delay grows, is multiplied by a factor of 1 over rho. So for the converse, again, it's reasonably straightforward. So you can say that, so we use the fact that sampling is non-adaptive. If the sampling is non-adaptive, and because we have a sampling budget of rho A basically, which means that most windows of size n over rho, if you take this the entire window of size A, and you look at chunks of size n over rho, most of those chunks will have at most n sample positions, right? Because otherwise you would violate the sampling constraint. Okay? So this is what the sampling constraint imposes. And the last thing that we use is the fact that if you want to achieve capacity, you have to sample the entire coverage, right? You cannot stop and make a decision here, for example. You have to go all the way to the end. Right? So if you combine those two, you immediately get the delay cannot be lower than n over rho. All right, so let's consider now the case where star does not belong to X. Okay? So if star does not belong to X, we cannot stretch anymore the covariates, right? Because this covariate expansion is costly. So what we do instead, we take the entire asynchronism window, we parse it into chunks of size n over rho, right? N over rho like this. And at the beginning of each chunk, we put a transmission period here. And the information transmission can be only in one of those specific slot of duration n. Okay? So for example, if new happens here, we start transmission here. Okay, we start the corresponding covariate there. Okay. Now, again, the analysis follows the case rho is equal to 1, and we get the extra penalty. So we have the delay now grows as so n over rho. The n over rho is the size of the chunks, but we have also to take into account the fact that if new happens anytime during an information transmission period, then we have to delay transmission to the next slot to be sure that the receiver can see the entire coverage. Okay. Right. So for the converse. So first, we convince ourselves that the coverage expansion is no more possible because it is costly. So this forces us to, so whenever we decide to send data, it has to be a burst of n symbols, the size of the coverage. Then the sampling constraint, similarly as before, for any chunk of, most chunks of size n over rho will have at most n samples. And so this is exactly the same as in the previous case, and from those two we get that that the delay is upper bounded by n over rho. However, we have this extra delay here because it may happen that communication that the new happens over a transmission period, right? In which case I had to wait this period and also this entire period here until the day. And this is n plus n over rho. Okay.
So like let's so a number for rho might be like 1/10.
Yes. Whatever, as more as you want. Yeah.
And so then the cycle is n over rho.
Yeah.
And you transmit n symbols every n over like how so.
Yes. So what you do,
are those symbols marking what when the receiver samples or when the
exactly. So this is those are the sampling periods. Those are the sampling periods, right? And the transmitter, whenever it has data that is available, it will start sending the code word over the next next transmission period. That's it. Okay.
Okay.
Yeah. And we see that because of that, so we have this. Each chunk here, each super period is of size n over rho, but we have this extra delay of n because if new happens here, if data is available here, I don't have enough space here. I don't have enough space yet to send my code word right there. So that what I will have to do is to wait the next one to send my data.
So how long is each chunk, is it n?
Is n over which one? This one?
Yes.
This is n.
This is
n. This is the code word length. Exactly, yes. This is n. Right, so n plus n over rho. This is n over rho.
So what is the big deal to include that star in the code word, I mean in the code word, in the symbols of code word, or not?
Yeah, so here we assume that the star is costly. So, sorry, the star does not belong to x, so there is no free symbol. Right? And previously we were using this free symbol, the zero cost symbol, to expand the code word at no cost. Here we cannot do that. Right? But even if we pick the symbol with the lowest cost, it will still cost us something. Right?
So if it is part of the code, I mean, if it is one of the symbols, then you assume that there is cost associated to that, or not?
Yes, absolutely. So yeah, I'm associating a cost to each element here. Okay? And I can use only, for my codebook design, I can use only symbols which belongs to that set. Okay. Now, if star belongs to this one, star has zero cost, then I'm fine. I can do code word expansion. If star does not belong to that set, all symbols have a positive cost. Yeah, hence, expansion is not possible.
So you're saying that X cannot contain symbols with zero cost?
Yeah. So if it is, it will be star. It will be star. Yes.
So somehow you're deriving a delay converse, which if I understand correctly says that reliable communication implies that you can't decode in less time than the following.
Exactly. Yes. This is the delay
But
converse.
somehow I guess I'm confused because the argument seems to be constructing a scheme.
No. I mean, no. This is just to build intuition. Actually, the converse works regardless of the scheme. Yeah.
So the scheme is just a.
So this is the achievability scheme. But for the converse, we show that whatever sampling strategy you choose, non-adaptive, okay, no matter what are the position of your samples, okay, you will never be able to get.
So this essentially is your achievability.
It's exactly achievability scheme.
Okay.
Yes.
So I'm reading the slide and just looking
Yes.
Okay. Right.
Should I change my slide?
I don't know, just under the achievability says delay converse. I'm like, well, wait, is this the
Yes.
converse?
Yeah. Okay. Yeah, because I didn't want to maybe draw another picture. So that's because what is a random coding strategy? So let's put the best one. Convince it is indeed the best one. Okay. Yeah. So what we saw so far is that regardless of rule, non-adaptive sampling strategies achieve the same capacity per unit cost as under full sampling. So there is no penalty due to reduced sampling. However, there is a penalty on delay. Right? The delay gets multiplied by a factor of 1 over rho. So if you are sampling 1% of the time, your communication delay will be multiplied by 100. Okay? So then the question is, okay, can we do better than that with, say, adaptive sampling? Right? So adaptive sampling will certainly achieve also the same capacity per unit cost as on the full sampling, because you can already get that with non-adaptive strategies. However, can we somehow reduce the impact on delay? Right?
But again, the question is, does the transmitter know what's the adaptive?
Well, he knows the strategy, but he won't know if the sampling, he knows the strategy, so he knows the rule, right? However, since he doesn't have access to the outputs of the channel, he doesn't know for sure when sampling will occur.
So you adapt to Y, you don't adapt to...
You adapt to Y, exactly, yeah. Yeah, okay. So before, for non-adaptive sampling strategies, the transmitter knows exactly the sampling times. Okay, for non-adaptive, it doesn't know. All right. So yeah, so we use this theorem. No loss in terms of energy. This is the same as in the previous slides, namely for a non-adaptive case. However, we see that the delay, the communication delay, is the same. So the communication delay with the sampling constraint rho and asynchronism exponent beta is essentially the same as on the full sampling. So you can achieve essentially the same energy efficiency as on the full sampling, and also the same delay as on the full sampling. Okay, so you can recognize the transmitted message as quickly, as quickly in terms of this measure of delay here, as quickly as if as a receiver that has access to all channel outputs, okay, with no constraint. Okay. Which means that you can, be any maximum, minimum, you can achieve maximum energy efficiency, reduce the communication delay, achieve minimum communication delay, same as with rho equal to 1, at a vanishing sampling rate. Okay, so this holds, this formula holds here regardless of rho. You can pick rho arbitrarily small, you get this equality.
So O of 1 means there's a constant.
It's O of 1 because all the results are asymptotic in the limit b tending to infinity. So this is just a constant that decreases. So this quantity here is a delay, right? The delay grows linearly with the number of bits that you are transmitting. This was our initial constraint, right? And this quantity is simply something that decreases, a constant, something that decreases as b tends to infinity. All right. So here is how the adaptive sampling strategy works. We start. The sampling strategy has two modes: the sparse sampling mode and the dense sampling mode. Okay. So the receiver first starts to sample sparsely at times that are multiple of 1 over rho. Okay. So when we are in the sparse sampling mode, we obviously satisfy the sampling constraint. Okay. Now, what we do, we attach to each code word a small preamble, okay, which will help the receiver detect the code word. Okay, so small preamble, which is negligible whose size is negligible compared to the overall size of.
Does the preamble consist of stars, or does it consist of X?
Or star would be a very bad choice, because star will induce the exact same distribution as pure noise.
Yeah.
Right? So you don't want star. You just want a symbol, symbols that differ from star.
Okay.
Okay.
So that means that you reduce the size of the code book somehow, because you know what the first few symbols are.
Yes, but very few. I mean, it's a negligible portion.
Also,
Yeah.
it's negligible.
It's negligible, yes. So, the size of the preamble, I'm calling here Sn, is little o of n. Okay, so small fraction.
It doesn't have to be kind of at least 1 over rho.
No, it has to be at least log n. I can go into those details at the end if you want, but okay, I can elaborate. So basically, rough intuition, I want Sn to be little o of n because I don't want any impact on energy. I don't want to achieve capacity per unit cost. And this constraint here, well, if I have a preamble that is too short, I will have many false alarms, basically. Yeah. Okay, so this will kill me. Okay, that's the idea. Okay. All right. So at each time, the receiver tries to identify the preamble. Okay. So the preamble is of size Sn. So I'm trying to I'm trying to detect the preamble based on the last row times the preamble size. Now, at each time, so I look at those row Sn samples, and I'm computing the empirical distribution. Okay? Now, if I am on the pure noise, this empirical distribution will look very close to pure noise distribution. Okay? However, so if the noise distribution is, if this empirical distribution is unlikely to have been generated by pure noise, okay, then I switch mode. Okay, I move to the dense mode and start sampling continuously for a period of duration n. At the end of this transmission, at the end of this period, what I do is two things. So either I am confident enough about the transmitted message, and then stop and output the message, or I say, maybe not. I'm not confident enough. Let me continue, and so I'm going back to the sparse mode, and I repeat. Okay. So this adaptive sampling strategy goes from sparse, dense, and hopefully, indeed, if you take the size of the preamble to be at least log n, but negligible with respect to n, then you can guarantee that you don't switch too often to the dense mode when you are observing pure noise, and so you won't violate the sampling constraints.
Somehow, like just trivially, if A is really, really large,
Yeah.
I mean, then it seems like you could be searching forever and making many, many, many mistakes.
Yes, so exactly. So the thing is that, okay, well again, if the size of the preamble is at least log n, this won't happen. It will happen with very low probability. Okay, so it's okay. Yeah. So okay. So this concludes the energy part. Now I don't know how much time I have.
We usually go about an hour. Oh, you're...
Yeah, but because we started a bit late, but some people may want to.
I think, please, you know, I mean, we started about.
This guy came from France, I think we can do it.
Well, I know I come from California,
so
that's
fine.
okay.
I mean, another 15 minutes is fine.
I can tell you.
I mean, people need to leave. They're always.
Oh, okay.
They will
Okay.
leave.
No, I mean, it will take roughly 10 minutes.
Yeah.
So,
Good.
all right. So we talked about energy. Okay. Yeah, and now I'm going to talk about latency. Okay. So far, let me just wrap up. So we focused on input-output energy consumption with a mild constraint on delay. Okay. So what we wanted is that the time when information is available and then when it is decoded, this should grow like order of bit. That's it, with high probability. However, what one can show is that for any cost-optimal strategy, namely for any strategy that achieves the capacity per unit cost, the expected delay here is huge, is proportional to A. It grows like A. Okay? So there is a big difference. So we control this quantity in probability, but when you look at expectation, it's doing very bad. Okay? So maybe if you have application that are, say, delay sensitive more than energy, instead of looking at energy efficiency, you look at delay, then we need maybe to change the efficiency parameter, and we need to be more stringent about delay. Okay, so this motivated us to consider a different figure of merit, which is a rate, not rate per unit cost, but rate respect to delay. Okay, and the delay will be the expected time between tau and nu. Okay, so this is the definition of rate. Right, I could have taken here instead of tau minus n, I could have taken the block length. This would be the rate respect to the transmission time. Here, this is the rate respect to the receiver time. Okay, I want really the receiver to very quickly to make a decision as quickly as possible to decode and output the transmitted message. Okay, so this puts a much higher constraint on the delay. Okay, but I'm ignoring energy, the energy issue here. Right? All right. So now I have the rates. Okay. And naturally, now for given uncertainty level A, I want to find the largest possible communication rate. Okay. Now A, look here. So the rate I'm scaling A exponentially with the block length, not with the number of bits that I want to transmit. Okay. So it's exactly the same. So you can go from one representation to the other, meaning you can scale either A with N or A with B. You can go from one to the other because there is a linear relationship between the block length and the number of bits that you want to transmit. However, all the results that I'm stating in this part are more naturally stated with this representation, okay, with this scaling. Okay? Fine. So R of alpha, so this is really a capacity for a given asynchronism level A or asynchronism exponent alpha, find the largest possible communication rate. Okay? Equivalently, I could look at the dual expression. You fix the communication rate and ask, what's the largest level of asynchronism for which I can still guarantee rate R communication? It's exactly the same. And same, the results that I'm going to state are more naturally stated with respect to this quantity here. Okay, the asynchronism exponent. Okay, so what is the largest level of asynchronism for which I can still guarantee rate R communication? Okay. So what we found so this is a problem that is still widely open, in the sense that so we have upper and lower bound on capacity, which don't match in general. The gap can be arbitrarily large. And we derive a certain property of this function alpha of R in the limit where the rate tends to capacity. And finally, we show that the suboptimality of training-based schemes in certain communication regime. So let me detail this. So I'm going to talk just about the lower bound. So the upper bound is a bit more involved, actually significantly more involved, and certainly technically much more interesting. However, it's a little bit cumbersome, and I would need much more time to address the upper bound. So let me talk about the lower bound because it has a very, very simple interpretation. Okay? All right, so we want the lower bound on alpha of R. So remember, alpha of R, this is the largest, this quantifies the largest level of asynchronism for which I can still guarantee rate R communication. Okay? Now, if I want to communicate at rate R, what does that mean? It means that the input-output needed information should at least be R. Right? Because even in the synchronous setting, I wouldn't need that much mutual information. Okay? Fine. So this gives me a set of inputs that are eligible for my codebook design. Okay? Now, among those X's that I can use for codebook design, which one should I pick? Right? So naturally, I want to pick a distribution, an input distribution that induces an output distribution that is as far as possible from pure noise. Okay? If you do this, I will help the receiver to discriminate between pure noise and the message, and the output of a message. Right? And this is exactly what this expression means. So the mean max of those two quantities here is essentially a pseudo distance between the noise output distribution and the output distribution that corresponds to message transmission. Okay? So we want those two to be as far apart as possible. Okay? So let me give you an example. So this is a very academic example with no application whatsoever. However, it points to something fairly interesting. And it's a very small thing, but I think it's quite surprising. So, let's consider BSC with crossover probability 0.1. Okay? And let's suppose that when nothing is sent, the receiver gets a Bernoulli process with a bias 0.1. Okay? All right. So here I plotted the upper and lower bounds on capacity. So this LB3 here is an old lower bound. It's always good to compare.
So when the star is 0, it's equally likely to be 0 one at the output?
No, it's biased, right? Yes, it's 0.9 and 0.1. It's a noise that is very much, it's a very biased noise.
Okay, so I see so both crossover probabilities are 0.1?
No, yeah, this is 0.1, 0.1, yeah. And 0.9, 0.9. It's a BSC.
Okay. Somehow I thought.
No, it's a BSC.
Yeah, it's a BSC.
Okay. It's a BSC, very biased noise. That's why, it would be more equivalent. The more natural setting would be to put 0, 1, 0, 0, 1, and then star here, and then map star to the 0 and to 1 with a 1/2 transition. Okay. Okay. So that's yeah.
Somehow
it's much more natural. That one would be much more natural.
Yeah.
Yes, but let me stick with that one because again, I want to point to something specific.
It's on-off key. But is that a good model for on-off keying?
Yeah, when you have 1/2, yes.
Yeah.
Yes. Yeah. So upper bound, lower bound. So this lower bound here was a weak upper bound. It's always good to compare with respect to weak lower bounds. That's why I put it here. So what this says is the following. Look at this regime here. Right? So C, this C here, is the capacity of the synchronous BSC. Is the capacity of this thing here. Okay? So you see that there is a gap. Look at capacity here. There is a gap here. Okay? Then this lower bound here doesn't vanish. It stops here. So what this means, it means that you are able to communicate at capacity, up to capacity, right? And still allow an exponential asynchronism. Right? right? Because alpha is positive, right? And A is exponential and is exponential with the rate alpha. Right? So you cannot tolerate, I mean, you can allow both exponential asynchronism and achieve capacity. And this may be surprising because, I mean, intuition for capacity, synchronous settings, essentially, so operating at capacity means essentially that we're saturating the channel in terms of hypothesis test. You can no more distinguish if you put any extra message, you won't be able to figure out what has been said. Okay? This means that you saturate the channel. But here, we are still allowing, the fact that we are able to operate at an exponential asynchronism, in the exponential asynchronism regime. This means also that that the receiver is not only able to discriminate the message, but also to do a hypothesis test over exponentially many possibilities, right? Because it can stop, because it can detect, but also, do both isolation of the message and detection at the right time. Right? So there is also this timing uncertainty, exponential timing uncertainty, which the receiver can overcome. And surprisingly, so this gap here is a property that actually is that holds for most channels. Okay, so only in very specific, for specific cases, we don't have this gap here. Okay, so here's the theorem. So for any channel, we have a gap, namely the alpha of r equal to c is strictly positive, unless there is one case, which is that the capacity, the noise distribution is the same as the unique capacity achieving output distribution of the synchronous channel. Okay, and that would be an example of such a channel would be yours. Okay, if you have the BSC, suppose that you have the same channel, you have the BSC, but you have the star here, and the star maps to 0 or 1 with probability 1/2. Okay, in that case, the output distribution conditioned on the star is 1/2, 1/2, right? And it is the same as the capacity achieving output distribution of the synchronous channel, which is also generally 1/2, 1/2. Okay. Okay, so now so the last thing I would like to mention is about training-based schemes. So the natural question is, okay, can we use how efficient are training-based schemes? Okay, so training-based schemes, the intuition is that I start information transmission with a pulse, with certain pulse, okay, and then send data. Okay, the pulse is meant to tell the receiver that I'm actually sending data. Okay, so the first thing we need to do is to define what a training-based scheme is, because we all have a good intuition about what this is, but it has never been really defined. So we're going to define training-based scheme as such. So a common sequence, so there is a common sequence of symbols across culprits. This is the preamble. Okay, and we are going to ask that the decoder's decision to stop at any time, okay, it should be based only on past S symbols, the size of the preamble. Okay? So if the preamble is of size, this is this size, then the receiver should stop just on past S symbols. Okay? So this is what we call a training-based scheme. And if you accept this definition, then you get the following theorem, namely that for training-based schemes, the asynchronism exponent always vanishes in the limit of high rate. Okay? Okay, so before we saw that in general it is possible to operate exponential asynchronism in the high rate regime. Here we see that training-based scheme always never achieve that. And there is never this little gap that we saw before at capacity. Always go to 0. Which means that training-based schemes are in general suboptimal, unless you are in this case that Roy was mentioning before. All right, so what this means, it means that to communicate at high rate under high asynchronism, synchronization and information transmission must be jointly performed. Each transmitted symbol should help detect, but also isolate the sent message. So here's a summary. So we propose asynchronous communication model which can be handled. Okay, so the other communication, the other information theoretic model for asynchronous communication is it's called the insertion deletion channel. So this is a different model which captures the situation where the channel itself eats and inserts random bits within the sent sequence. And for that model, very little is known. Okay, capacity is still an open problem, etc. But the two models, the one I presented and the insertion deletion channel, are very much complementary. Why this? So in the insertion deletion channel, it is assumed that, so the receiver knows that the transmission of information starts right from time one. So the receiver knows that the transmitter starts sending data immediately. Right? However, the information transmission period, that one is variable. Okay? Here it's the opposite. The receiver doesn't know when information starts being sent, but conditioned on the initial transmission period, the receiver knows how long transmission will last. Okay? Because the duration is always fixed. There is no extra insertion or deletions. Okay? So it's really a complementary model. So we evaluated the impact on energy and latency due to asynchronism. We saw that with non-adaptive sampling strategy, you are able to achieve the asynchronous capacity per bit cost on the full sampling. However, there is a penalty of 1/rho, and this penalty of 1/rho in delay can be overcome if you consider adaptive sampling strategies. And which means, again, you can be maximal cost energy efficient, minimize the detection delay, and sleep almost all the time. And finally, for the delay part of the talk, I focused on capacity bounds and showed the suboptimality of training for in the high-rate regime. So there are several open issues. For the delay case, better capacity bounds. As I said, the upper and lower bounds are very far apart in general. Efficient code construction. Also, all the codes that I have, all the achievability results that I stated were based on random coding. Okay? But there is no code construction as such. Okay? Another open issue would be the finite block length analysis. Okay? So to happen, all those results are asymptotic. What happens if you back off and say, okay, now A is this much, the block length is this much. Okay, what is the real impact? And finally, I mean, of course, I mean, there are many. This was all what I mentioned was for point-to-point communication. Obviously, a big open problem would be to address the network problems. What happens when you have several nodes operating asynchronously one with each other? And finally, bit asynchronism. Okay, so the model assumes that you have a common clock basically between the transmitter and the receiver. What happens when you don't have this? Okay, and this is also a major challenge. So, so this is essentially it. Here are references. In blue are the papers where contain essentially what I have said, and all the black ones, the other papers refer to similar problem setups. So for example, 3 and this one. So those two were considered a slotted version of the problem, right? So they consider, so in principle, in the model that I presented, the receiver, so there is the overlap. So the receiver can stop at the time where it has observed only a part of the transmitted message. Right? This could happen in principle. So, and dealing with those situations where the receiver sees only a part of the transmitted message may be difficult. I mean, it is difficult analytically, and this is what makes the numbers quite difficult to come up with. And what you can do, you can simplify the problem, assume that communication starts only, I mean, happens in only one of consecutive blocks of duration n. Okay? If you do that, then essentially you get rid of this problem of partial overlap, and you can actually, and this is how we derive some of the lower bounds, some of the upper bounds on capacity. Okay, assume a slotted marginal E, and those two works, for example, this one and this one did error exponent analysis for this model. Let me mention also, for example, those two works here, which are sort of the first work which address asynchronism in the information theoretic limits of in the context of networks, okay, and asynchronous communication. Yeah.
So do any of these address multiple access?
Excuse me?
Do any of these address multiple access?
So we addressed a little bit the multiple access case, but we have a very partial. We did a little bit, so meaning the following. So communication is very sparse, right? We are sending a little piece of data, out of A, which is, A is very big. Now, if I have two transmitters, there is no problem, right? It is very unlikely that the messages will overlap with each other, the transmission periods will overlap with each other if A is very big, right? So with 2, with 3, etc., if the number of users is, say, polynomial in the block length, then it's fine, because it's immediate to show that there won't be conflicts, right? Then it will never happen that the two transmitters send you data at the same time, okay? But what happens under heavy traffic, right? So we have many users, and let's scale as A, for example, and that when they send data, that can be overlapping data. So this is essentially completely unknown.
So somewhere along the way, I lost track of new, the starting time.
Yes.
Like some of the results, like did you make some assumption about it, or is there
New is uniformly distributed. This is the assumption.
over
However,
the whole 0 to A?
for 0 to A. However, you can easily, you can. It's not critical. You can easily extend most of those results to non-uniform settings. Of course, you have then to define what is the limiting distribution, because A, it's a one-parameter distribution. We know what is a growing A, right? But yeah.
So,
Yeah.
what happens if new occurs at A? You don't have any time to decode.
Well, the overall experience lasts A plus n minus 1, if you want. Okay? That's the end. Okay.
But also A is exponentially large compared to.
That's true. Yes. So there won't be any. There won't be. You can even. Yeah, you can cut the tail if you want.
So in the adaptive sampling scheme, since nothing depends on rho, how do we choose rho? Like the sampling rate?
So you will choose it as little as possible. Yes. Then this is one of the issues. Is what we'd be interested to know is to investigate is the finite length analysis, right? Because it's true that you can keep rho arbitrarily small, and you get asymptotically the same results, but again asymptotically, right?
All right. Let's thank our speaker.